I want to make it very clear. I am not a low carber. I am also not a low fatter. I am not an anything. Okay? I am a real food guy. Okay? And I think all real food works. It's what we do to the food that doesn't. I want to make that clear. And I'll show you why I think that as we go. The other thing I want to say is you can't solve a problem if you don't know what the problem is. And we're trying to solve the problem. And I'm going to tell you, we don't have one problem. We have three. And you can't solve three problems unless you know what the three problems are. And that's what we're going to delineate today. Three separate problems. They overlap, but they're separate. They all fall under this term, metabolic syndrome. And you think you know what that is. You don't know what that is. And that's what we're going to talk about today. So, first of all, I did write these two books for the general public. I am the chief science officer of a nonprofit here in the Bay Area called Eat Real, where we're trying to promote real food. We praise the good. We certify restaurants, hospitals, cafeterias, school districts that procure, market, and sell real food. We are teaching fourth graders to cook in the East Bay as a model for being able to change the educational paradigm across the state and then hopefully across the nation. And I'm also the chief medical officer of a startup for-profit called BioLumen Technologies, where we're trying to develop a bioengineered answer to this metabolic syndrome epidemic. If anybody's interested, we can talk about it later. None of that will have any impact on this talk. All right. If you look at preventable causes of cardiovascular death over time, you can see smoking, down. Blood pressure, down. Cholesterol, down. Physical activity, up. We should be reaping a health benefit. We are not, because obesity is up and diabetes is through the friggin' roof. In fact, this is a paper that was published in Lancet in 2000, and it projected that we would go from 151 million diabetics on the planet in 2000 to 221. So that would be an annualized inflation rate of 3.88%, if that were true. What we actually ended up seeing in 2010 was that there were 285 million. That's an annualized inflation rate of 6.55%, double the rate that we thought we would see. And in the next 4 years, to 2014, 422 million. And that's an annualized inflation rate of 10.3%. In other words, while we're trying to fix the problem's getting worse, maybe because we're causing the problem. Duh. WTF. Now, you all know that. That's why you're here. This is the friggin' choir. Okay? I love you guys, and all my friends are in the room, and we're going to have a love fest, okay? But you can't fix the problem if you don't know what the problem is. Here's the problem. Nonalcoholic steatohepatitis is now the leading cause of liver transplant in America. Okay? A disease that hadn't even been identified before 1980 is now the leading cause of liver transplant and is actually the biggest epidemic, even bigger than type 2 diabetes. And if you look at the medical costs, so we're looking in the red at hospital costs, in green at physician costs, in blue at pharma costs, they do not add up to the total medical costs because the rest of it's going to the care and treatment of chronic metabolic disease. And you can't fix the problem if you don't know what the problem is. There are two inconvenient truths that the medical establishment refuses to deal with. The first, there is no medicalized prevention for chronic metabolic disease. There's only treatment. And those treatments, to be honest with you, don't really work. Oh, they treat symptomatology. Yeah, they'll get your blood glucose down. Yeah, they'll get your blood LDL down. Yeah, they'll get your blood pressure down. And you die anyway. And you die on disability. The second is, you can't fix healthcare until you fix health. You can't fix health until you fix diet, and you can't fix diet if you don't know what the hell is wrong. These are the two inconvenient truths. Started here, okay? Basically, everything Gary told you is exactly right, and this was the culmination of that. The US dietary guidelines, right? And that's what we got instead. Okay? We traded one set of diseases for another. We traded cardiovascular disease for metabolic syndrome. And this is why. And this is just another way of saying what Newberg said. Okay? But Coca-Cola said it in their words. Everybody remember the Coming Together campaign of Coca-Cola back in 2013? It was played on every football game the entire year. And this is a direct quote. Beating obesity will take action by all of us based on one simple common sense fact. All calories count no matter where they come from, including Coca-Cola and everything else with calories. In other words, calories are fungible. Doesn't matter where they come from. They all enter one big engine, and the engine burns them exactly the same way no matter where they come from. And therefore, why pick on our calories? Go pick on somebody else's calories. This was their method for assuaging their culpability. So, they say it's about calories. They say it's about obesity. Is it? I'm going to give you 5 separate reasons why this is not true. Here's one. Here is a scattergram of all the countries in the world. Obesity prevalence on the x-axis, diabetes prevalence on the y-axis, and you would look at this and you would say, well, very clearly, Dr. Lustig, there's a correlation, and there is. Agreed, there is a correlation. But correlation is not concordance. They're not the same. Because there are countries that are obese without being diabetic, such as Iceland, Mongolia, Micronesia. And there are countries that are diabetic without being obese, such as India, Pakistan, and China. India and China today have an 11% diabetes rate, and they're not fat. We are the fattest nation in the world, have a 9.4% diabetes rate. If diabetes is just a manifestation of obesity, how come they have more diabetes than we do? Problem number 1. Problem number 2. Obesity is increasing worldwide at the amortized rate of 2.78% per year, yet diabetes is increasing worldwide at the rate of 4.07% per year. If diabetes is just a subset of the larger subgroup of obese individuals, how come it's going up faster? Problem number 2. Problem number 3. Here we have from JAMA all the increase in prevalence of type 2 diabetes diagnoses over a 25-year period, and you can see it going up over here on the left. Now take a look on the right where it's stratified by weight status. And you'll notice that, too fast. 25% increase in the obese, but there's also been a 25% increase in the normal weight population. If diabetes is due to obesity, how come the normal weight people are going up just as fast? Problem number 3. Problem number 4. Anybody here an endocrinologist? Aside from David Ludwig, who knows this better than I do? Okay, 1 or 2. Okay, these are the Little Women of Loja. They are an Ecuadorian cohort that have a defect in their growth hormone receptor. They are very short. They are very fat. You can see them. Okay? And they are protected from heart disease, diabetes, and every other chronic metabolic disease. They are protected. So here's their glucose tolerance, and here's their insulin response to a glucose tolerance test. Look how much lower their insulin levels are than normal. They are insulin sensitive. They're fat, but they're insulin sensitive. And if you look at their baseline data, it's all better. Okay? Whether it's their HOMA, their insulins, their lipids, so that over here or here, you can see they're all better. They're healthier. They're healthier and they're fatter. And the reason is because it's their adipose tissue versus their liver, and they're not the same. And my colleague Ethan Weiss at UCSF has developed knockout mice for each of those to show that how growth hormone works on those two are completely opposite. And so these, Little Women of Loja are actually protected against metabolic disease unrelated to their weight. So this is what I'm trying to tell you. Here's a Venn diagram of the entire US population. 30% obese, BMI over 30, 70% normal weight, BMI under 30. Everyone in the room is in one of the 2 circles, and you know who you are. The standard mantra from the doctors and the dietitians and the Institute of Medicine and the National Institute of Health and the Surgeon General and the White House and Congress and the food industry is 80% of these obese people, they're ill, they're metabolically ill. They get type 2 diabetes, hypertension, lipid problems, cardiovascular disease, cancer, dementia. It's these 57 million people. They're fat and they're sick because they're fat. And therefore, if they would only just diet and exercise, we could solve this problem. That's what they say. Bullshit. Why is it bullshit? Sorry, I'm from New York. I can't help it. Okay? Why is it bullshit? It's on the slide. Come on. It's on the slide. Well, it is true that 80% of 30% are metabolically ill. I don't argue that. That is true. But that means 20% are not. 20% are metabolically healthy. We have a name for them, MHO, metabolically healthy obese. We study them to try to figure out how come they didn't get sick. Conversely, 40% of the normal weight population have the exact same diseases as do the obese, and they're not obese. Normal weight people get type 2 diabetes, hypertension, lipid problems, cardiovascular disease, cancer, dementia, too. And they get it for the same reason, they're just not fat. Well, if you get it unrelated to your weight, then how can it be about behavior? This looks like exposure. And it turns out there are more thin sick people, 67 million, than there are fat sick people, and the thin sick people are calling the fat sick people the problem. More bullshit. And I'll prove it to you. So, any radiologists in the room? Good. Here are two CT scans through two abdomens of two equally weighted people. Notice trunk fat 12.8. One's healthy, one's sick. Which one's the sick one, A or B? B, right, because he's got visceral fat, right? The other guy, he's just got big love handles, subcutaneous fat. That's the fat you can see. Visceral fat, that's the fat you, quote, can't see, right? So obesity is not the problem. Metabolic syndrome, and we'll define it now, is the problem because that's where all the money goes. Obesity actually doesn't cost very much. Okay, it's all the diseases that go with it that cost 75% of all healthcare dollars. And here's the list. And diabetes being the sentinel disease of this. Now, what is metabolic syndrome? So here are count them, 6 separate medical societies, professional medical societies, and they've all defined metabolic syndrome differently. So what's that telling you? Telling you at least 5 of them are wrong. And maybe all 6, right? Because it's a syndrome. Duh. That means it's not a disease, because it's a syndrome. Keep that in mind. Okay? And I was on this task force in metabolic syndrome in children. We didn't even try to define it because we didn't even have the cardiovascular events to hang our hat on. The reason that all of this jumble, mush, garbage has been thrown at you is because everyone's seeking to define metabolic syndrome phenomenologically with cutoffs. You know, greater than 90th percentile for blood pressure, greater than 95th percentile for triglyceride level. Where did that come from? These are skewed kurtotic unimodal distributions. They're not bimodal. There's no place to draw the line. So you're telling me 90th percentile is metabolic syndrome, but 89th percentile would not be metabolic syndrome? Now, how effed up is that? I mean, that doesn't make any statistical sense whatsoever. Okay? It's actually much easier to define the metabolic syndrome mechanistically. That is, where's the insulin resistance? The one thing that everyone agrees on is that metabolic syndrome is associated with this phenomenon called insulin resistance. The question is where and how and why. That's where we're going. So if you look here from 1970 to 2014 at a group of healthy Americans, oral glucose tolerance testing shows that euglycemia is maintained in healthy adult Americans. There's no change in the glucose tolerance curve of healthy adult Americans in those 44 years. 44 years. I can't count today. but take a look at their insulin levels in order to maintain that glucose level. Here's 1970 and here's 2014 up here. 2 to 4-fold more insulin released for the same level of glucose. That's called insulin resistance. And if you're impaired glucose tolerance, it's even worse. So in the past 40 to 50 years, our need for insulin has increased 2 to 4-fold. So that's our question for today. How did we get 2 to 4-fold more insulin resistant? And by the way, coming back to that leptin resistance question I mentioned earlier, insulin's the cause of leptin resistance. The higher your insulin goes, the less well your brain can see its leptin, which of course then makes you eat. So even though you're fat, your brain thinks you're starving. The higher your insulin goes, the more weight you gain and the hungrier you get. That's what we're talking about. Now, how does this happen? And this is where the 3 comes in, the 3 different diseases. This is what you learn in medical school. This is what I learned in medical school. This is what those of you who went to medical school, this is what you learned in medical school. You get fat. You ate too much, you exercised too little, you got fat. The alternative hypothesis says, well, your insulin did that, but you still got fat. And it starts with your fat cell. Your adipose tissue is ground zero. And because your adipose tissue gets fat, it starts making cytokines like TNF-alpha, IL-6. You get adipose tissue inflammation and macrophage recruitment, and et cetera. And all of those cytokines then go to the liver, make the liver sick, which then causes the liver to increase gluconeogenesis, and so you get increased hepatic glucose output, which then feeds back because now you've got a higher blood sugar to deal with, and your islet cells therefore have to make more insulin in order to keep your blood sugar constant, the graph I showed you before, and that drives more fat. And so you end up with this vicious cycle, but it started in the fat. And then the muscle comes along for the ride. Originally, Jerry Shulman thought it was the muscle. Now that he's got a 3 Tesla magnet that can actually measure what's going on in the liver, he agrees it's not the muscle. He thinks the muscle's a bystander, not the cause. Everybody got that? That's what you learned. More bullshit. So, here's the relationship between BMI, that is sub-Q adiposity, and insulin sensitivity. Now you'll notice there is a very clear hyperbolic relationship. So the heavier you get, the more insulin resistant you get. Agreed. But at any given BMI, you could be insulin sensitive or you could be insulin resistant. Just like we talked about before, metabolically healthy obese. Here they are, right here. So just being fat has nothing to do with it. Second problem, okay? So obesity is potentially a way to make this happen, but not necessarily the only way. I would actually argue that it's actually a rare way to make metabolic syndrome happen. I think it's about 10, maybe 15% of the total. Not very common. Second problem, it's called stress. Now, stress causes release of norepinephrine throughout the entire sympathetic nervous system. No arguments there? Now, norepinephrine is lipolytic. Norepinephrine goes to the adipocyte and causes hormone-sensitive lipase to be activated, which then takes triglyceride and turns it into free fatty acids, and those free fatty acids then exit the fat cell. So adrenergic activation, sympathetic activation from stress, from acute stress, causes fat mobilization. You should lose weight, but you don't. Why? Anybody? This is the paradox that has been basically killing this whole field for the last 15 years. The answer is Zofia Zukowska, who passed away. She was a brilliant physiology researcher. She was head of anatomy and neurobiology at Georgetown. She figured it out. Yes, it is true that acutely sympathetic neurons release norepinephrine, which then cause thermogenesis and cause fat mobilization. That's all true acutely, but not chronically. In fact, chronic stimulation of anything causes death. Chronic overstimulation of anything causes death. And so adrenergic neurons have a thermostat built into them. They have another hormone neuropeptide called neuropeptide Y. When you release norepi initially in response to an initial sympathetic outflow, you just get the norepi. But if you chronically stimulate, you end up with the norepi and the neuropeptide Y. And the neuropeptide Y's job is to actually shut down the effects on the beta-adrenergic receptor and actually end up leading to lipid storage and actually causing pre-adipocyte proliferation and adipocyte differentiation in order to put that energy somewhere else. So in other words, acute stress causes lipolysis, chronic stress causes lipogenesis because of neuropeptide Y. And then there's this third problem. Here we have a guy who has metabolic syndrome to beat the band, and he's not fat. In fact, he has too little fat. Not too much fat, he has too little fat. This is a disease called lipodystrophy, where for some reason, the transcription factors that drive fat cell development aren't working right, and they don't develop the fat that they should. It tends to be X-linked autosomal dominant. HIV can cause it. Minimal visceral fat, normal or excess facial fat. They have Cushingoid facies, a dorsocervical fat pad. It's the only place they seem to have fat. And they have acanthosis nigricans, and they have metabolic syndrome to beat the band. They can get thousands of units of insulin and still not get their blood sugar down. But they have too little fat. Not too much, too little. So let's compare lipodystrophy with obesity. Fat mass, lipodystrophy down, obesity up. Leptin, lipodystrophy down, obesity up. Adiponectin, a protective cytokine. Lipodystrophy down, obesity also down. Maybe that's important, could be. Inflammatory cytokines like TNF-alpha, IL-6. Lipodystrophy down because there's no fat cells to make it. Obesity up. And if you have lipodystrophy, you have metabolic syndrome, big time. Whereas if you have obesity, maybe you do, maybe you don't. So what is this telling us? It's telling us metabolic syndrome can occur from too much or too little fat, because it's not the fat that counts. Not the fat you can see anyway. What do these two things share? Well, they share this thing called insulin resistance. Everything comes back to this phenomenon. What about insulin resistance? What kind of insulin resistance? Where? How come? What do we do about it? Agreed. That's what this is all about, and that's why you're sitting here, is to understand this phenomenon. So let's reframe the debate from what I've told you thus far. Whoops, sorry, what happened? Oh, obesity does not cause metabolic syndrome. It is a marker for the metabolic dysfunction that attends metabolic syndrome. It's just another marker, just like impaired glucose tolerance is a marker, just like high triglycerides is a marker, just like high blood pressure is a marker. Okay? Obesity is a marker also. It's the result of the problem, not the cause. Obesity is a red herring, because everyone's at risk for metabolic syndrome, including normal weight people, as I showed you before. Okay? So obesity is not enough. Insulin resistance is not enough, because obviously not everyone has lipodystrophy. What kind of obesity, what kind of insulin resistance, in which tissue, and are all insulin pathways affected equally? Those are the questions we have to answer, and I have 14 minutes and 22 seconds to do it. This is the most important slide I'm going to show you. Okay? This is from Fabrini et al. From Sam Klein's group. They were the first people who stuck people in a scanner, and instead of measuring big butt fat, sub-Q fat, and big belly fat, visceral fat, everybody had done that before. What they did, because they were cool, was they measured big belly fat, visceral fat, and big liver fat. Got it? Visceral versus liver fat instead of sub-Q versus visceral fat. And what they showed was that when you looked at their insulin dynamics here on the y-axis, turned out that when you held the liver fat constant, the visceral fat contributed nothing to the pathology. The visceral fat was along for the ride. It was the liver fat that made all the difference. The liver fat dictated the insulin dynamic problem. So, okay, liver fat is the problem. Where'd the liver fat come from? Well, that's over here in gray. Non-systemic fatty acids, non-systemic. Now we know where systemic fatty acids come from. They come from lipolysis of peripheral adipose tissue, and that can actually be from saturated fat, and you need to know that. The paper just came out from Iki Järvinen just 5 days ago that saturated fat can actually increase that adipose tissue lipolysis, bringing more fat back to the liver. Or it could be from dietary fat. So it can be from adipose tissue lipolysis or dietary fat. But non-systemic, where did that come from? Well, it turns out that's being made right in the liver, de novo, through a process called DNL, de novo lipogenesis. And my colleague Jean-Marc Schwartz is here, and he will be talking to you at length about DNL tomorrow and its central role in this process. Turns out, this fatty liver is the real problem, because fatty liver is worldwide, even in normal weight people. It is the liver manifestation of metabolic syndrome. And the question is, how'd you get there? Well, if you look over here, women versus men, men have more of it even at normal weights, and diabetics have it even at normal weights. In fact, in the Korean population, non-alcoholic fatty liver disease is the precursor to type 2 diabetes. It comes first. So here's how you need to think about this problem. Here's what we call an MRI Fat Fraction Map done by my colleague Sue Norlowski at UCSF. Notice obese, love handles, right? But take a look at that guy's liver, 2.6% fat. This is a metabolically healthy obese, MHO. Nothing wrong with this guy. He'll outlive you. Now here is what you more likely expect. Here's love handles. Take a look at this guy's liver, 24% liver fat. That's non-alcoholic fatty liver disease. That's metabolic syndrome. Agreed. That's not good. Now take a look at this guy. Notice? No love handles. Take a look at that guy's liver, 23%. This guy's just as sick as this guy. Thin sick, fat healthy. They're not the same. Okay. So we need to understand how that liver got sick. Now, as it turns out, Ron Kahn at Joslin at Harvard constructed for us 8, count them, 8 separate tissue-specific insulin receptor knockout mice to ask the question, which organs matter? Which organs make the disease? And here are those 8. And it turns out 6 of them are actually protected from obesity. They have their own diseases. Not like these are good, but they don't get fat. All right? My favorite, by the way, is this one at the bottom, the glomerular podocyte insulin receptor knockout mouse, the PDRCO mouse. The insulin receptor has been lifted out of the kidney. Everywhere else, mouse is totally normal. That's all they did was take the insulin receptor out of the kidney. Got it? Normal blood sugars, normal glucose tolerance tests, normal insulin response to glucose, normal insulin dynamics. The worst diabetic nephropathy of any animal model ever. Normal glucose. Diabetic nephropathy. How does that happen? Anyone? Because it's not the glucose that made the nephropathy. It's the insulin resistance in the kidney that made the nephropathy. And we know that because you can find the microalbuminuria in metabolic syndrome patients before they ever get glucose intolerant. And you know that. Think about it. Okay? I hope I'm hitting you over the head. I'm trying really hard to hit you over the head, to bang some sense into you. All right. But, go back. The only 2 insulin receptor knockout mice that actually get fat are liver and brain. The LRCO and the NERCO mouse. Okay? Now, the NERCO mouse is another 2 hours. We don't have time for that today. So maybe someday Sean will invite me back and I'll talk to you about that. But today we're going to talk about the liver one, okay? The liver. So here's what insulin does in the liver, okay? Pancreas makes insulin. There are 2 pathways after insulin binds to its receptor. The first is the phosphorylation of this 4-kit protein called FOXO1. When phospho-1 gets phosphorylated, it excludes it from the nucleus and therefore prevents the transcription of gluconeogenic enzymes. This is therefore decreasing hepatic glucose output, thereby reducing total glucose in the blood, keeping glucose levels normal. That's how insulin lowers glucose. Got it? The second pathway is here, stimulating this transcription factor here called SRABP1C, sterol regulatory element binding protein 1C. This is the transcription factor that drives that phenomenon I just talked about, de novo lipogenesis. So when insulin meets a sensitive liver, you lower your glucose and you take your fat, you put it into triglyceride, you attach ApoB, and you export it out as serum triglyceride. And so it enters the bloodstream, and then insulin peripherally at the fat cell will clear it. And this is how you stay metabolically healthy, but can put energy into fat cells. Got it? This, for lack of a better word, is good. Now, let's take that insulin receptor out of the liver. So the IRKO mouse. Okay? So now this animal only is missing the insulin receptor from the liver. Well, pancreas is making insulin great guns to beat the band, trying to make the liver do its job, but it can't because the insulin receptor is gone. So the FOXO1 doesn't get phosphorylated, and so gluconeogenic enzymes go sky high, and so you end up with hyperglycemia, diabetes. Fair. In addition, there's no insulin receptor to stimulate SRBP1C, so your triglyceride levels are low. High blood glucose, low triglycerides. Is that metabolic syndrome? It's diabetes, but is it metabolic syndrome? No. This is not metabolic syndrome. What is metabolic syndrome? Well, it's this. Here's insulin. You can't phosphorylate FOXO1, so glucose is high, diabetes, okay. But somehow, some way, through some mechanism, that SRBP1 is still going great guns because it's making triglyceride to beat the band, releasing that triglyceride, and so you end up with hypertriglyceridemia as well. Now, the $64 zillion question is, there's only one insulin receptor. It's been knocked out. So how do you get one pathway working and not the other? How do you dissociate those two pathways when you only have one insulin receptor and you've knocked it out? This is the Nobel Prize for metabolic syndrome. Whoever figures this out will win the Nobel Prize. Everybody got it? So, in order to explain metabolic syndrome, we are looking for a ubiquitous factor that promotes obesity, preferably visceral adiposity, and in particular liver adiposity, promotes hypertension, and induces this phenomenon called selective hepatic insulin resistance, dissociating these two phenomena in the liver so that you block FOXO1 to promote gluconeogenesis and therefore hyperglycemia, but at the same time can stimulate de novo lipogenesis to drive hypertriglyceridemia and atherosclerosis. Does anybody want to make a guess what that ubiquitous factor might be? Fructose. Oh my God. Nobel Prize. So, as Gary will tell you, fructose is toxic. He wrote a whole article about it. He now wrote a whole book about it, The Case Against Sugar. And we wrote this Nature comment back in 2012, The Toxic Truth About Sugar, which I wrote with my colleagues from UCSF, Laura Schmidt and Claire Brindis. And the question, of course, is everyone says, what, come on, really, Dr. Lustig? I mean, sugar? I mean, it's been around for thousands of years. It's natural, comes out of the ground. It helps keep food from spoiling. It's 4th of July and apple pie and Valentine's Day. I mean, aren't you just guilty of hyperbole? Well, so we have to look at the word toxic, toxicity. What does it mean? The degree to which a substance can damage an organism, right out of the dictionary. Anybody got any problem with that definition? Now, notice the definition does not distinguish acute toxicity from chronic toxicity. So we have acute toxins like sarin and ricin and cyanide and VX gas, parts per billion, keel over and die on the spot. Okay? No one would argue those are acute toxins, right? But we also have chronic toxins like carbon tet, arsenic, benzene, tobacco smoke. They don't kill you today, but they'll kill you. Just takes a little longer, right? They're still toxins, just not today. Now, in order for me to prove that fructose, this sweet molecule in sugar, is a chronic dose-dependent hepatotoxin, I have to meet 4 criteria. I have to show that fructose is an independent risk factor for these diseases with time, not just correlation. I have to show it's exclusive of calories, because otherwise calories are toxic, in which case Coca-Cola is right. I have to show it's exclusive of obesity, because then obesity is toxic, and I've just shown you normal weight people get this too. And I have to establish causation. Correlation will not do, right? Everybody knows the difference between correlation and causation? You better. Because if you don't understand the difference between that, you should not be practicing medicine. All right, now there are a whole bunch of critics of this, as you know. They're out in force. Food industry employs all of them. They say, animal models, not human studies, and you have to give excessive doses of fructose in order to see these effects, not relevant to humans. So I will limit my discussion today to human data only, human consumption only, in doses routinely ingested by humans, maybe your children. Okay, here's what's happened to our consumption of sugar. Our ancestors getting fruits and vegetables out of the ground with the occasional honey got about 4 pounds of sugar per year. Here's the growth of the sugar industry. C&H and Domino, Texas, Hawaii, Louisiana, finally reached stabilization where price equaled demand. Here's the rationing of World War II, came back to the same level afterwards. And then we had 3 things happen. Number 1, we had high fructose corn syrup. Number 2, we had the dietary guidelines. And number 3, we had the change in our farming practices, all happening at the same time in the 70s. We had Nixon telling us, make food cheap. And that drove things all the way up. The point is that fructose is not glucose, because a calorie is not a calorie. They're not the same, and I'll show you that they're not the same. In fact, fructose is 7 times more likely than glucose to form advanced glycation end products, AGEs, which are very specifically detrimental and toxic to cells and humans. Fructose does not suppress the hunger hormone ghrelin. So David is in the room. He and Kara Ebling did this study years ago. If you take a kid and you preload them with a soda and you let them loose at the fast food restaurant, do they eat less or do they eat more? They eat more. They took on 150 calories, they eat more. How come? Because the brain didn't recognize that eating. So clearly not the same. Acute fructose does not stimulate insulin. It does chronically because it causes insulin resistance, but it doesn't cause insulin secretion, which actually means that the brain doesn't know that you ate. And you also don't get leptin out of it immediately. So that also doesn't activate the sympathetic nervous system. And finally, hepatic fructose metabolism, liver fructose metabolism, is completely different from that of glucose. They bear no relation to each other. And I'm going to show you that chronic fructose exposure alone can cause metabolic syndrome. Now, it may not be the only cause of metabolic syndrome. I'm not suggesting that. But it is clearly a primary cause and an identifiable cause and a malleable cause, something you can fix. So here's the metabolism of glucose coming into the liver cell here, and virtually all of it ends up as glycogen, liver starch. That's what your liver wants to do with glucose. That's why marathoners carb load before a race, is to make glycogen. Glycogen is non-toxic. A little bit of it will seep down here via the Embden-Meyerhof glycolytic pathway to pyruvate, enter the mitochondria here, generate the TCA cycle, ATP and carbon dioxide, the reaction of life. A little bit of it maybe gets thrown off as citrate, exits the mitochondria through a process known as the citrate shuttle, and then that citrate can act here in the cytosol as the nidus and the start of this process over here, driven by these 3 enzymes ATP citrate lyase, acetyl-CoA carboxylase 1 fatty acid synthase. These three enzymes are de novo lipogenesis, new fat making, and look what they're under the control of, our friend SREBP1. Got it? But how much of this VLDL you think you're going to make out of that glucose? Not a whole lot, because it went to glycogen. And most of it ended up actually outside the liver because 80% of the glucose got chewed up by all the other organs in the body. But here's what happens to fructose. 100% enters the liver because only the liver has the GLUT5 transporter. So the whole bolus ends up there. So you're dealing with a whole lot more substrate. First step, fructose 1-phosphate. Turns out that fructose 1-phosphate activates this enzyme called C-Jun N-terminal kinase 1, which then inactivates the insulin receptor. Now you've got hepatic insulin resistance. In addition, fructose 1-phosphate will come down to the mitochondria, and now you've got a lot of it because all of it ended up in the liver. The TCA cycle is overwhelmed. The mitochondria are overwhelmed. And remember this term, mitochondrial overload. When your mitochondria are overloaded, then the citrate comes back out through that citrate shuttle, and now you got a lot of citrate to drive this pathway to VLDL. So the VLDL gets exported, and here's the hypertriglyceridemia of sugar consumption, and that can serve as a substrate for obesity. It could also serve as a substrate for atherogenesis. In addition, some of the fatty acyl-CoA won't even make it out and will precipitate as a lipid droplet. Now you got non-alcoholic fatty liver disease. Not only that, but because you have hepatic insulin resistance, you can't phosphorylate that FOXO1, so now your blood glucose goes up, now you got hyperglycemia too. So what do you got? You got hyperglycemia, hypertension here because of the nitric oxide reduction because of uric acid, which is the endogenous inhibitor of endogenous endothelial nitric oxide synthase. Hepatic insulin resistance, dyslipidemia, muscle insulin resistance, obesity, atherosclerosis, and leptin resistance because of the insulin resistance. What do you got? You got metabolic syndrome. But that's only problem number one. Now comes problem number two. On this slide, there are 5 pictures of food. They all share one thing in common. What is it? Nope, not carbs. Does that look like carbs to you? No? Huh? Right, they're all brown. They're all brown. That's right, okay? The common link is the Browning reaction, known as the Maillard reaction. Non-enzymatic glycation is why glucose binds to hemoglobin to form hemoglobin A1C, right? So here's how you need to think about this problem. You can roast your meat at 375 degrees for an hour, or you can roast your meat at 98.6 degrees for 75 years. The answer is the same. You are browning. You are browning right now. You are browning even as we speak. And if you had orange juice this morning, you are browning 7 times faster. And if you don't believe me, here's newborn rib cartilage, nice and white, and here is 88-year-old rib cartilage, nice and brown. You're all browning. It is the aging reaction, and the faster you brown, the quicker you die. Period. Well documented. We know this. Slam dunk. Now, here's why. So here's glucose. Here's in the linear form. Here's an aldehyde group, and here's an amino group. You put an aldehyde and amino group together, you get a shift base, which then decomposes to form this covalent linkage, which we can measure then as hemoglobin A1C. And every time this reaction occurs in cells or outside, okay, you generate a reactive oxygen species, a little oxygen radical, which can then do damage on its own. Can cause lipid peroxidation, protein denaturation, cell aging. Oxidative stress. You've heard it? Oxidative stress. It's part of living, but it's also part of eating badly. Right? Okay. And every time that happens, you have to quench it. You have to quench that reactive oxygen species with an antioxidant. In the liver, that would be glutathione. In other cells, it could be other things like vitamin C or vitamin E, but glutathione in the liver. Why does this happen? Well, so here's glucose over here in the linear form. Here's glucose in the ring form. Here's the space-occupying model. Notice, 6-membered ring, hydroxymethyl group sticking up axially, not bothering anybody. This is what we would call a happy compound. At pH 7.4, 37 degrees, 99.2% of the glucose in your body is in the ring form. Only 0.8% is in the linear form where this aldehyde group is available to bind to proteins non-enzymatically. Everybody got that? Now, it is true that your serum glucose level is high, or higher, I should say. You know, it's in the 60 to 100 range. So it's going to happen. I mean, you can't not have it happen. But the lower you keep your glucose, the less it'll happen. Fair? Okay. Now, down here, you got fructose. So here's the linear form, here's the ring form, here's the space-occupying model. Notice, 5-membered ring. 5-membered ring. Ionic strain trying to break this thing apart because it's wound tightly. Notice 2 hydroxymethyl groups, axially in the same plane, button heads. Allosteric interaction, driving this ring apart. So at pH 7.4, 37 degrees, 97% of the fructose is in the ring form, 3% is in the linear form, compared to 0.8% for glucose. And this reactive keto group is just as reactive as the reactive aldehyde group. And so it will happen 7 times faster with fructose than with glucose. And I can prove it. You can do this experiment at home. Take 2 test tubes, add fructose, glucose, and then add water, add some bovine serum albumin, equal amounts, cap it with some parafilm, and put it in the sunlight. And each day you come back and you put it in your home spectrophotometer and you read out the fluorescence. Okay, and this is how fast the glucose does it, and this is how fast the fructose forms that reaction. 7 times faster, 100 times the number of reactive oxygen species that have to be dealt with by an antioxidant. What happens when you don't have enough antioxidants? That's called NASH. So how do we know this is true? Well, we have empiric data. So here's the consumption of sugar in the US population, adult population. This is a histogram of the percent of calories as added sugar done by Frank Hu's group. The median is at 18%. The red line through the center is the hazard risk ratio for cardiovascular mortality in the same population over the same period of time. The inflection point is at 15%. So what does that mean? It means that more than half the US population has an increased risk of dying of a heart attack because of their added sugar consumption. This was done in Europe. It's called the EPIC Interact study. It's the same as our NHANES. Okay? What they wanted to ask was, does sugar beverages predict diabetes? And the answer is, if you take into account the energy intake and the BMI, 29% increase in risk for diabetes. Same for meta-analyses, looking at the same thing. And here's sugar beverages, and here's fruit juice, showing the same effect. Everyone says fruit juice is healthy. Take a friggin' pill. Our group, my colleague Luis Rodriguez, my grad student and my dietitian, took the NHANES adolescent database and asked the question, does added sugar consumption in the adolescent database predict metabolic syndrome? When we get up to the 4th quintile, there's a 10-fold increase in metabolic syndrome. We did an econometric analysis looking at sugar availability instead of sugar consumption. And what we saw was that only sugar gave us a signal. Yeah, I know, I'm at the 0, I got it. Only sugar gave us a signal, and it was a significant signal. Here's the adjusted association of sugar with diabetes prevalence around the world. Here's the take-home message. Only changes in sugar availability correlated with changes in diabetes prevalence. If a country had an extra 150 calories per person per day within its borders, diabetes prevalence went up a total of 0.1%. But if those 150 calories happened to be a can of soda, instead, diabetes prevalence went up 11-fold, 1.1%. These data actually meet the Bradford Hill criteria for causation, for causal medical inference, the same level of proof we have for tobacco and lung cancer today. Because we showed dose, more sugar, more diabetes. We showed directionality, longer sugar, we showed duration, longer sugar exposure, more diabetes. We showed directionality, those countries where sugar went up, more diabetes, those countries where sugar went down, and there were 10 of them, less diabetes. And finally, precedence. Something has to precede something else to be causative, right? 3 years. 3 years. Whenever sugar changed in a country, diabetes changed in the same direction 3 years later. That's causation. And now we have the proof.
because we have the interventional proof. And this is the study that my colleagues at Touro University and UCSF did. Jean-Marc Schwartz is here, and will address this study tomorrow in part as well. What we did was we took 43 kids from our obesity clinic at UCSF, and we figured out what they were eating at baseline. We studied them at baseline, and then we catered their meals for 9 days. No added sugar. Now, if you do that, you're going to take 350 to 400 calories out of their diets, in which case they might lose weight because they'd be in caloric deficit. We didn't want them to lose weight. We wanted to keep them the same weight. So we had to substitute something that was equicaloric. We gave them refined starch. Got it? We did a starch for sugar, a glucose for fructose exchange in the vernacular. We took the pastries out, we put the bagels in. We took the sweetened yogurt out, we put the baked potato chips in. We took the chicken teriyaki out, we put the turkey hot dogs in. Everybody got it? We didn't give them good food, we gave them crappy food. We gave them processed food. We gave them kid food. Food kids would eat, but it was no added sugar food. And we gave them a scale. And every day we'd call them up on the phone, what'd you weigh? And if they were losing weight, eat more! To keep their weight constant over the course of the 10 days. And then we studied them again. All their baseline levels got better. These will be online, so you'll be able to see all of them. All of them got better. We wanted to measure de novo lipogenesis, so we gave them C13 labeled acetate, which gets incorporated into VLDL, and here's how fast the reaction reduced. In 10 days, we cut it in half. Here's their glucose tolerance test, 8% reduction in glucose area under the curve. Remember, we're giving them more glucose. They should have a higher glucose tolerance. They had a lower glucose tolerance. And the reason is because their insulin levels went down because now they're insulin sensitive. We turned them from insulin resistant to insulin sensitive. And most importantly, the fat depots. So notice the subcutaneous fat, the big butt fat, no change because we didn't let them lose weight. The visceral fat, down 7%, that's good. Liver fat, down 22%. With no change in calories, no change in weight, and the change in the liver fat predicted the change in all the metabolic improvements. So, cartoon. Fatty liver, it's brown, VLDL being made, 9 days of fructose restriction, the liver fat's down, the DNL's down, the VLDL's down, and the insulin kinetics have reversed. We reversed their metabolic syndrome. And we didn't even have to change their calories. All we did was change the food. Got rid of the sugar. That's it. So we have causation, not correlation, causation for sugar in 4 diseases: diabetes, heart disease, fatty liver disease, and tooth decay. We have correlation for sugar in cancer and sugar in dementia. We're working on those. So I would propose to you a different model of insulin resistance. Starts here in the liver. You get liver fat instead, and fructose being a primary driver of that. Because of the fatty liver, the liver now is sick. You end up with increased hepatic glucose output. Now you've got beta cells making extra insulin, and that drives excess energy into fat cells, driving the obesity. But if you get rid of the liver fat, the insulin goes down. If the insulin goes down, then the patient loses weight. And that's what we did at UCSF in our obesity clinic every friggin' day for 17 years. Now, just so you don't think I'm fructocentric, there are actually 4 items that are all metabolized the same way in the liver. Do the same thing with de novo lipogenesis. Trans fats do this, but we know that and they're coming down. So that's not the answer anymore. Branched chain amino acids, leucine, isoleucine, valine, all essential amino acids. Protein powder, okay? Corn-fed beef, chicken, fish. High in branched chain amino acids. You guys are low carb USA. Branched chain amino acids also do this. Alcohol, but kids don't drink alcohol, but boy, oh boy, do they consume fructose. So what do these 4 foodstuffs have in common? Number 1, the liver's the only site for energy regulation. Number 2, they're not insulin regulated. Number 3, there's no glycogen pop-off, and the mitochondria become overwhelmed. And that is what metabolic syndrome is. Mitochondrial overload in whatever tissue you're looking at. If it's in the kidney, you got kidney disease. If it's in the heart, you got heart disease. If it's in the liver, you got liver disease. Got it? That's what this is. I'll skip this for time. And there's no drug target for this. Mitochondrial overload promotes de novo lipogenesis, leading to insulin resistance, metabolic syndrome. Mitochondrial overload releases those reactive oxygen species, leading to cell dysfunction, aging, and death. The only options are reduced substrate availability. That's called diet. But not any old diet, and certainly not a weight loss diet, and certainly not a processed food diet. Reduce hepatic flux. That's called fiber. Fiber reduces the amount of glucose and fructose that get absorbed from the duodenum into the liver, thereby keeping your liver safe. And if you don't absorb it in the liver, then it goes further down the jejunum, where the bacteria will chew it up. The microbiome will get it. So just because you ate it didn't mean you got it. And all of these energy calorimeters, all these whole body calorimeters, they're not studying humans. They're studying the human microbiome unit. They don't know what's happening in human cells versus bacterial cells. You got to feed your bacteria. You got 10 trillion cells in your body. You got 100 trillion bacteria in your intestine. You're just a big bag of bacteria with legs. You got to feed your bacteria. Fiber's the way you feed it. Now, Low Carb USA doesn't exclude fiber, but it doesn't promote it either. You need to. Okay? In fact, what I hope I've shown you is that there is not one problem. There are three. Three problems. Three metabolic syndromes. The first one, due to subacute fat, the one everyone knows, the one everyone talks about, the one everyone thinks is the only one. We can call that the bucket hypothesis. You got a bucket. You fill the bucket. You overflow the bucket. You get problems. Okay. I think it's rare. Visceral fat. Call that the stress hypothesis. That's why depressed people have metabolic syndrome. They're losing weight, but they're increasing visceral fat. You can see it on MRI. And finally, liver fat, which we can call the mainlining hypothesis. And I mean that very specifically since fructose is addictive. And that's another story. And the thing is, we knew it. We knew it 50 years ago. We knew there was a problem, but we were driven off course through some of the things that Gary talked about earlier, and because the Sugar Research Foundation actually made us go off course on purpose. Because they sponsored a whole program within the Sugar Research Foundation to basically obfuscate the truth. It started in 1965 with a literature review published in New England Journal by Fred Stair, the head of nutrition at Harvard School of Public Health, and his assistant, Mark Hegstead, who became the head of the USDA, which singled out fat and cholesterol as the dietary cause of coronary disease and downplayed the evidence that sucrose was also a risk factor. The SRF set the review's objective, contributed articles for inclusion, and received drafts, and the SRF's funding and role were not disclosed. It's all been a big fraud, the whole thing. The last 50 years of nutrition information in America is a big fraud. All of it. And that's why diabetes has continued to increase, not just in prevalence, but in incidence, because we actually put the Bunsen burner underneath it to make it boil over, because we were lied to. Now, you guys know that. The problem is you got to get everyone else to understand it too. So, is sugar public enemy number one? Trans fats used to be. But now they're gone. So now this is public enemy number one, because we could do something about this. Okay? And you wouldn't even have to go low carb. You just have to go low sugar. It's called real food. So with that, I want to thank my collaborators, many of whom are in the room today, okay? At UCSF, at Touro, San Francisco General, Hastings, Berkeley, Health Evolution Partners, and I'm happy to answer any and all questions. I'll be around. Please feel free to come up. Thank you, sir, for your attention.